Hello, everyone. My name is Dr. Tanya Rusi. It's my pleasure to welcome you to the webinar Quantum Computing with Real-World Impact. And now it's my pleasure to introduce Dr. Anthony Ransford. Tony was the lead architect of Helios, and he's now working on all of our large-scale architectures. Tony, take it away.
Thanks, Tanya. Hi, I'm Tony Ransford. I had the pleasure of working on this project from its inception to its launch in November. And today I'm going to be telling you why Helios is the most powerful and accurate quantum computer in the world. So in the beginning, we'll kind of go over quantum computing basics, a background on trapped ion quantum computing and the QCCD architecture. Then we'll dive into the Helios architecture and all the things that make the system work at the lowest level. After that, we'll talk about benchmarking, which is how we validate that Helios is the most powerful quantum computer in the world. And then we'll look at some applications that we ran on Helios after we validated it. And after that, we'll discuss how a lot of the key innovations in Helios fed forward to our future architecture with larger scale, higher fidelity quantum computers. So let's start with our development roadmap. And there's two things I want to point out in the slide. One is that we've been doubling the qubit number with each subsequent quantum computer we've released. That holds true with Helios, but it's worth noting that we need to accelerate the number of qubits we're putting in these machines, and I'll tell you all the things that Helios is going to help us accelerate that scaling. The second thing I want to point out about this slide is that H2 was arguably the best performing quantum computer before Helios. And as you'll see later in the talk, despite doubling the number of qubits, we actually improved several key component level metrics, fidelities on the system of Helios, and also system level performance is improved over our previous generation quantum computers. Helios has a pretty large feature set. It has everything that the previous systems had, all connectivity, mid-circuit measurement, real-time QEC decoding, and many other features. But we've also added a lot of features with the eyes towards scaling to larger systems. This includes leakage measurement, dynamic transport, qubit allocation, real-time, and arbitrary control flow. And a lot of that is enabled by our real-time engine, which runs in parallel with the quantum computer. It allows us to execute classical tasks while the quantum computer is running. Okay, hopefully people are excited after that introduction. I'll get into the main part of the talk. First of all, why do we build quantum computers? We know classical computers are fundamentally limited. They can only do certain problems that we know quantum computers can do better. But I think maybe more importantly, every time we've given society a new tool or technology, think about classical computers or microscopes or telescopes, we've gained a greater understanding of the world around us. And this has always led to innovations that couldn't have been predicted immediately after that new technology came about. So I sort of see Helios and really where the community is in general in quantum computing at this inflection point where we're just now sort of getting new knowledge to people, and I'm excited to see what that leads to. What is quantum computing? I guess we'll break it down at the lowest level. Basically, classical memory is built on transistors, and they can store zeros and ones. So if you have classical memory with only 3 transistors, you can store one number somewhere between 0 and 7. But in quantum computers, you can store superpositions of those numbers. So if you have 3 qubits, you can store all 8 of those numbers simultaneously. And that's one difference, but this leads to a kind of a scaling of the state space you have, where in a classical computer, if you had a billion transistors, and you wanted to double the memory, you'd need to add another billion transistors. But if you have a system like Helios that has 98 qubits, just adding one more qubit kind of doubles the accessible states. If it were that easy, we'd be off to the races, but it's a little more complicated than that. We live in a classical world, so we can only put in small state space classical inputs into our quantum computer. Then we need to explore this exponential space, and we need to find an algorithm that focuses that down to an answer that we can read out on our classical computer. This seems like a hard problem, and it is, but luckily these algorithms exist. Examples are Shor's, Grover's, quantum chemistry, and there's many more. Yeah. So now let me tell you about the Helios hardware. Let's start with the basics. We use trapped ion qubits in our quantum computers. They use the hyperfine structure of the atomic qubit. And all of the interactions are generated by controlling the optical states of these qubits. So we excite electrons with lasers. So we use this all optical laser control, and that really means that the laser technology matters. And that's sort of what motivated us to switch which qubit we use in Helios from the previous generation Quantinuum quantum computers. I like this chart on the left from our laser supplier. It shows how much available laser power you can get at different wavelengths. And you can see barium is actually much more in the visible and some transitions in infrared. And so you just have access to much more laser power to scale up. And then a terbium, which is deeper in the UV, which is our previous qubit. Not only do you have more laser power and it's more cost effective, the visible and IR allows us to leverage telecom technology. And as we start moving towards delivering this light with integrated photonics, that's going to be a real enabler. So all of our gates and measurements are done with lasers. Our 2-qubit gates are done with a pair of lasers, and those generate entanglement. We do single qubit gates to create superpositions with a different laser, and measurement as well that projects the state. So trapped ion quantum computers are made out of microfabricated chips. So these are fairly standard fabrication techniques. And we use electromagnetic fields to levitate the ions above these microchips. And we can move the ions around by adjusting voltages on these patterned electrodes. So on the right is kind of a cartoon of that situation. Imagine a chip with patterned electrodes. And you can see if we want to do a gate, say, on this green ion, we can move that green ion into a zone where a laser is, perform that gate. But then if, say, we want to do a 2-qubit gate between the green and red ion, we can move that green ion over next to the red ion into a 2-qubit gate zone and perform a 2-qubit gate. Similarly, if we want to do a measurement, we can move all the qubits away from the measurement zone to minimize crosstalk, and we can do a measurement in that zone. It's a little more complicated in Helios than these cartoons, although this is still kind of a cartoon, but this is what the Helios architecture looks like. On the left, there's this ring storage, which we think of as kind of a random access memory. This is where we store qubits until we need to use them. We have a cache where we can put pre-sorted qubits in that are getting ready to have quantum operations done to them. We have a quantum logic region where 2-qubit, single qubit, and measurements happen, as well as cooling. And we have another storage ring on the right where ions can move off to while we process more qubits. As an atomic physicist, I I really like this picture because this is kind of the real thing. These are real individual qubits, single trapped ions levitating above the surface of a trap, and there's 98 of them. It's a pretty incredible picture. So moving these ions around, we kind of we need to sort all 98 qubits in order to maintain our all-to-all connectivity, which we have on Helios. And that's built out of several transport building blocks. The first one I'll talk about is this rotate, which gives us sort of random access to any qubit in the ring. I'll mention that every qubit, barium qubit, has a buddy ytterbium that always moves around with it, and we use that ytterbium for cooling, and that cools the barium sympathetically. The storage ring can be rotated clockwise or counterclockwise, which means we can efficiently grab the nearest qubit to this junction right here if we want to. And the other really neat thing is you would think you need a lot of electrode control to rotate all 98 of these qubits, but actually the waveforms are pretty repetitive across the ring, and so it only takes us about 3 signals to perform this rotate operation to move the qubits either clockwise or counterclockwise. Second building block is the junction. This is maybe the most crucial and one, and there will be junctions in all of our future architectures. So this is an enabling component for future architectures, but the junction, an ion can enter the junction and it's allowed to stay in the storage ring, or it can be pushed out into either the upper or lower cache region. It can also be spit out into the cache region in either a BY or YB order. So we have full control of these qubits, where they go, when they go where. The final major building block is linear shifts. And so as qubits come in sorted from the cache, we can perform linear shifts to the right to move qubits into the logic region, where we can perform 2-qubit and single-qubit gates. And after that's done, we can linear shift them farther to the right into the storage legs. One impressive thing about this is we also do massive broadcasting for these linear shifts. And all this leads to, despite Helios being a much larger chip with many more pattern electrodes, there's 1,228. It only takes 273 signals to fully sort all 98 qubits. And this is pretty similar to the numbers in our much lower qubit systems, H1 and H2. And the signals per qubit has dropped pretty dramatically in Helios. The logic region of the trap is kind of where all the quantum magic happens. Initially, there's 16 qubits that are shuttled into the logic region in a batch, we call it, at a single time. After that happens, the qubits can be split apart into left and right qubits, where we can perform single qubit gates. We then merge these qubits, do some cooling, and then perform 2-qubit gates. We actually perform 2-qubit gates on only 4 of the zones, and then we shift the crystal and perform 2-qubit gates on the other qubits. So the sort of slow operation here is the cooling, but the complex control operation is the 2-qubit gates. So by making the cooling occur in all 8 zones, we get the parallelism speed up. But by doing 2 qubits and just 2-qubit gates in just 4 of the zones, we don't lose any speed, but we have to control less of our more complicated laser signals. This is a really nice animation of the sort happening. So because of the real-time engine, this sorting can happen in parallel with quantum operations. So the ring spins around, spits the qubits out. And while cooling's happening on this batch, we're pre-sorting all the qubits out of the ring for the next batch. Then laser operations happen, single qubit and 2-qubit gates in this quantum logic region. And the pre-sorted next batch of 16 comes in as those first batch move into the storage legs. And this process is repeated 6 times until all qubits in the ring have been processed with an arbitrary connectivity. During all of this, we perform, like I said, the real-time sorting, but we also perform phase tracking for any variations in beat field across the trap. And this plot here kind of shows that you can imagine this straight line being the quantum computer clock speed. And these circles here are the scheduled tasks by the real-time engine that's running in parallel. And you can see that the classical computer can schedule all gates, calculate the sort algorithm, do any dynamic branching, mid-circuit measurement. It can schedule all of those tasks ahead of the quantum computer, all in real time. One new feature of Helios is a thing we call ternary measurement. And normally when you read out a qubit, you get a 0 or 1. But it turns out the structure of barium allows us to check whether we have any leakage during the quantum operations. And we can return to the user a 0, 1, or an L if the state has leaked. This is kind of important in error correction, because if you can detect a leakage error, that turns it into what's called an erasure error. And those are sort of the easiest to correct in quantum error correction. Okay, now that we know how that works, let's look at benchmarking. We benchmark at the component level and at the system level. And so first I'll talk about the component level. When you build one of these machines, kind of the first thing you do is do state preparation and measurement, which is preparing a qubit state and making sure that you can tell it's in that state. Sort of the easiest thing to do. So the way this works is we randomly prepare each qubit in a register in either 0 or 1, and then we check whether we've done that correctly, whether we actually did that. And these bars show how often we were wrong. And so the spam error in the system is about 5e minus 4, and this is certainly the best state preparation and measurement of any programmable quantum computer. And it's also a 3x improvement over H2 at launch. And then we also characterize this new ternary measurement. It says leakage measurement here, but it's the same thing. And we see similar span fidelities even using this ternary measurement. The second component we characterize is single qubit gates. And we do that via a process called single qubit gate randomized benchmarking, or SQRB. And how that works is we prepare each qubit in the register into a state, and then we start just performing random single qubit gates with random angles and phases. And we do many of them. And we accrue an error each time that happens, and that error scales exponentially. We fit an exponential curve, and so basically the probability of the right answer as you go out to very long sequences decays exponentially, and we can backfit what the error from one of these single qubit gates is. And these are the results for 16 qubits in the logical register of Helios, and we get an average error about 2.5 e minus 5, which again is the best fidelity in the industry for single qubit gates on a programmable device. For 2 qubit gate benchmarking, we perform something that's very similar, except that we do pairs of qubits and we perform entangling gates. But the process is the same. We perform random entangling gates many times in a row, allow the error to accumulate, and fit that probability to a decay. And from that, we can back out the error on a single one of these 2 qubit gates. Doing that, we get an average error of about 8 e minus 4. This is more than a factor of 2 improvement over H2. And furthermore, this on a system this size, this is the best 2 qubit gates in the world. The last thing we do, it turns out that there's errors associated with doing this random sort and transporting these ions around, mostly due to how well we track the magnetic field changes. And so how we characterize that is we interleave the SQRB with random all-to-all sorts. So we do a single qubit on all 98 qubits, actually, even though 8 are shown here. We do a random 98 sort. Then we do some more single qubit gates, and we vary how much transport we're doing as a function of a single qubit randomized benchmarking experiment. And each one of these transports accrues error. It's worth mentioning too, we do this with a 0-angle 2-qubit gate so that we also include the ground state cooling and basically every error cost you would need in a real circuit. So all the errors included. When we do that, this is sort of an amazing plot for me to see the first time. There's 98 lines here. So it just felt good to see all 98 qubits. And you can see that when we interleave much more transport, like in these blue lines, the errors accrue faster versus when we have only like one layer of transport and the errors accrue at a slower rate. And we also are able to check on leakage because we have this new turn area measurement. And so we can see what contribution of this error is coming from leakage with this new tool. From that data, you can extrapolate what we call a memory error, which tells you how much error you're getting per qubit per full layer of sorting, of arbitrary sorting. And you can see that at the moment, our error rate is lower than say our 2-qubit gate error, but it's still a contributing factor and something we actively work on. The last thing we characterize, so in our systems, we can measure qubits, we can reset them, and we can reuse them mid-circuit. However, turning a laser on always has a chance that, or turning any signal on really has a chance of causing crosstalk with other qubits. So this is something we want to characterize. And the way we do that is we have a probe qubit that we prepare in some state. And then we have a target qubit that we measure many, many times in a row, hundreds of times in a row. And then we see if there was an error on that qubit, this spectator probe qubit. On the left is a plot that shows an example of that. We're measuring these top 4 qubits. And in principle, there should be no errors imparted on any of these qubits in the bottom. Of course, eventually there is with enough measurements. But you can see actually the mid-circuit measurement crosstalk is quite good. It's something like 2e-4 per mid-circuit measurement in the logic region. So think of this 0 through 15 as the logic region of the trap. But we still have 98 minus 16 qubits in the ring. But those are very far away and they see very little crosstalk actually. So our global crosstalk is almost an order of magnitude lower than our local crosstalk. Okay, so we've characterized all these components. If I just did that, I wouldn't believe I had a quantum computer yet because I want to make sure it can run algorithms and arbitrary circuits. One of the ways we do that at Quantinuum is via this random circuit sampling. This kind of was made famous by Google as this quantum supremacy task. That's classically computationally difficult. We do it with a little bit of a different flavor. We have all-to-all connectivity. So instead of using some nearest neighbor interaction, as was done in those systems, we perform random single qubit and random 2-qubit gates across all 98 qubits. And then we randomly sort them and do another random single qubit and 2-qubit gate across all 98 qubits. And we do that with varying depths. So we vary how many of these things we do. You might ask, how do we know we got the right answer? Because we don't know what the answer should be because we can't simulate it classically. Well, we play this trick called mirror benchmarking, where we actually only run half of the RCS, and then we reverse it in the back half so that the answer should be exactly the same as the answer we started with. And you might think that some nefarious error might get reversed by just repeating the same circuit, but in reverse. But we play a lot of tricks to make sure this doesn't happen. We can do different compiling and different sorting schemes so that the errors get scrambled on the way back versus the way forward, to convince ourselves that what we're doing is the right thing. But I would say maybe even more convincing is that this plot on the left is the circuit depth of the RCS circuit versus fidelity. And if we fit a decay curve there, we can extract this value that we call the effective 2-qubit error. But this includes every single error I've talked about in this talk: single qubit, memory error, 2-qubit error. This is every error to do a full 98-qubit arbitrary single qubit and 2-qubit gate. And these numbers are consistent with adding up the errors I talked about at the component level, which is nice to see. It means we really understand the quantum computer. Just to impress upon everyone how complex these RCS circuits are, there's this plot that we made for the paper that's pretty nice to see. As we increase the complexity, you can ask how hard would it be, say, Frontier, one of the best supercomputers in the world, to get the same fidelity as Helios. And you can ask that kind of in two ways. You can ask how long would it take Frontier to do, and the answer is very, very, very long. But you can also ask what's the power consumption required if you just scaled Frontier up to an arbitrary size. And there's this kind of neat result that it would require the power of all stars in the observable universe to do it in the same amount of time as Helios does in. So it truly is a powerful quantum computer. Okay, I believe now that we have a working quantum computer. Probably nobody wants to program it by typing in the 2-qubit and single qubit gates. So for Helios, we've created a new programming language, an application programming language that is very Python-like and allows a user to program their quantum circuits using a lot of these features like dynamic qubit allocation and conditional branching, but in a very abstract way where you don't think about the low-level stuff. That feeds into Quantinuum Nexus, where job submissions, circuit optimization, a lot of that stuff happens, and that passes it down to either any of our Quantinuum machines or to our simulator, Quantinuum Selene. Okay, let's talk about applications that were run on Helios. All three of these applications I'm going to talk about were run during the private preview before the launch in November. We had about 3 months where we were racing to run all these jobs. And the first one I want to talk about is called certified randomness. And the idea is to generate random numbers with a quantum computer, because with a quantum computer, you can prove that the numbers are actually random. You might want to ask why you want to do that. I like this book from the 40s where there was this book of 1 million random digits that people were seeding their Monte Carlo simulations with. You would just turn to a random page in the book and seed your Monte Carlo simulation. So people care about random numbers. They also are important cryptography. You want to make sure that you're not generating bad random numbers. But many random numbers are derived from physical systems. The famous one is lava lamps is how some random numbers are generated. But these can always be biased. So if you're really paranoid about your random numbers, you may want to certify that they're random from a quantum computer. The way this protocol works is a customer will give us a very hard quantum circuit. We'll solve it as fast as we can and return it. And they'll give us many quantum circuits, actually, and we'll solve them all as fast as we can and return them. And of course, these are too hard for them to verify, even with a supercomputer. But what they can do is they can spot check them. And they can spot check them, 1% of the circuits. on the supercomputer, which is still hard and computationally expensive. But then they can say that either we have a supercomputer that's 100 times more powerful than the one they spot checked us on, or that we're giving them truly random numbers. They don't need to trust us. And one interesting fact is that kind of this time scale sets a distance of how far, if we had 100 times more powerful supercomputer, how close it has to be to us just based on the speed of light. And so this time really matters. I guess that's what I'm trying to impress is to improve this setup, you want to make this time as small as possible. And so we have this real-time engine on Helios that runs classical compute in parallel with the quantum compute. So our theorists came up with this clever idea of maybe we don't actually have the customer pass us the entire circuit in this short time window, but they can beforehand give us most of the complicated circuit. We run all of that, and at the very end, they tell us what measurement basis to make in. And it turns out that's sufficiently complex to ensure that we have a quantum computer in the same way that having the whole circuit did. But it's really drastically shrunk down the latency from the customer to us to back, because now we just need to run this last set of gates and measure it. And you can see because of that, we've dropped our latency in Helios from H2 in these types of circuits from about a second to about 10 milliseconds or tens of milliseconds. And this directly transfers to how much money you need to spend on the supercomputer to verify that these samples you receive are actually random. Cool. The second application I want to talk to you about is some experience we did involving superconductivity. So this was news to me, but apparently there are experiments done where if you zap a piece of yttrium barium copper oxide with a ultra-fast laser for a couple picoseconds, it'll actually superconduct at 300 Kelvin for about 2 picoseconds. It's not clear what the mechanism is here, and it turns out that it's very difficult to model classically. But perhaps if we knew what this mechanism was, we could learn something about superconducting in general, which would be pretty exciting. So for those of you not completely familiar with what we're looking at here, we need to create a microscopic model of this system and look for what are called pairing correlations. So we need to look at whether both electrons in this material tunnel site to site together, whether they're correlated in pairs. And on the left here is kind of a short range scenario, which you might not expect superconducting to be happening in. And then on the right is where those pairing correlations have long range interactions or long range tunneling. And so on Helios, we're able to simulate this by writing down a Hamiltonian for this Fermi-Hubbard model, which is sort of the toy model that describes this situation. It turns out classically, people have simulated this with up to 20 sites, but it required an enormous amount of compute power. On Helios, we can simulate on the quantum computer with up to 36 sites, so quite a bit larger. And once we do that, we can look at what happens to the tunneling, the pairing correlations before and after we apply a laser pulse. So we can generate this Fermi-Hubbard model without this extra laser pulse. And then on the right, this is actual data from Helios. On the right, you can see after generating this light pulse on the quantum simulation, we can see long-range pairing correlations. Yeah. So have we solved this? Well, not quite. This still isn't sufficient to understand what's leading to this superconducting mechanism, and a lot of that reason is that The fidelities on today's quantum computers just simply aren't good enough. You can see that down here somewhere in the 10 to minus 5s is where we think sort of the fidelity correlates to how long of a laser pulse we can look at. So we're kind of here in this picosecond regime, and we'd like, or in this femtosecond regime, we'd like to be in this picosecond regime. But we still did learn something that couldn't be simulated on a classical computer. And we're continuing to make better quantum computers. But furthermore, I think this sort of points to something that's known in the field that we just need to get to fault-tolerant, error-corrected quantum computers, especially large-scale ones. Yeah. So how do we get better fidelities? The answer is error correction. The idea behind error correction is that you take many physical qubits, you encode them in such a way that you get one logical qubit of which you can detect errors on and correct those errors. So on Helios, also during the private preview, we did some quantum error correction to show that we could get improved fidelities by encoding these physical qubits into logical qubits. There's some technical stuff on the slide, but I'll just describe what this notation means. The 80 means we used 80 physical qubits. The 48 means that we made 48 logical qubits. And this distance 4 means that it's not just an error detection or error mitigation scheme. You can correct one error and you can detect another error. So this is a fault-tolerant error correction scheme. The way we created that was by concatenating two error detection iceberg codes, 862 and 1082. And you can think about that in these, you only have, say, the rows, and then you don't know which column it happened in, and this one you only have the columns, and by concatenating this, you can sort of pinpoint where the error occurred at in both row and column. Doing this, we got a span fidelity on all 48 logical qubits of 99.99, which is 5x better than our physical span. And we also created a GHZ state out of these 48 qubits. And it was actually like 50 times better than the logical or than the physical GHZ state we create. And yeah, I've been really impressed by the team that worked on this and these results. I don't think anybody really thought that you could get 48 logical qubits out of a 98 qubit machine. I would say that, I just want to mention that even though that takes 80 physical qubits, we actually use all spare 18 qubits. So we use all 98 qubits, and the other 18 are used for Scylla. Okay, looking forward, back to our roadmap. So we're right here in 2025 on Helios. And as we look forward on our roadmap, we need to get to Sol and then Apollo. And what has Helios helped us mitigate? Well, we have junction transport, and you can kind of see from these pictures that there will be many, many junctions in these future systems. Our baseline for the future systems is barium qubits, so we can check that box. These will need lots of parallelization schemes, and we showed that in our logic region. We now have this new language, Guppy, that we can abstractly program these systems and do quantum error correction with. And we have this real-time control where we can schedule things, we can do arbitrary logic, conditionals, and we also have this gate streaming feature. So I think a lot of these things are going to directly feed forward, or maybe all of these things are going to directly feed forward into our roadmap and help us scale faster. With that, I'd like to thank everybody at Quantinuum. This was a massive effort. If you look at this hardware paper, there's 200 authors, and there's probably many more people that helped and contributed. So all of Quantinuum, a huge thank. This has been an amazing project that I've been lucky to work on. And then I'd also like to thank the private preview team, our partners at JPMC who ran the certified randomness paper, or the certified randomness circuits. And also, they did another experiment that I didn't have time to talk about, but it's in this paper right here. And then Henrik and his team in Germany that work at Quantinuum with this superconducting pairing correlations paper. All of them did an amazing job over the private preview. The last thing I want to say is I want to advertise these programs that we have at Quantinuum. So the first one is QNet, the Quantinuum Network. And this is a way to get early access to news, things coming up in Quantinuum, things like talks like this. Also, there's a yearly meetup. So if you use that QR code on the left, you can get access to that. And then on the right is our startup partner program where if you're a startup in the quantum ecosystem, you can get access to our quantum computers. You can help us co-promote our hardware and software, and you can get support. And that's that QR code on the right. And with that, thank you all for your attention.
So with that, let's wrap it up. Thank you so much, everyone, for attending. And thank you so much, Tony. That was just a really excellent talk. Let's give Tony one more round of applause.
Thanks, everyone.